Okay, so I was tasked with talking about Chris's early contributions. And I went onto my bookshelf and I found these tech memos from MIT. These, you write your thesis at MIT and they turn them into tech memos. And you can see this one back here from Chris. It looks pretty ratty. I actually did use it a lot in my own work, so I appreciate Chris's contribution there. This is the front page of his master's thesis, I guess. But anyway, these studies do some important papers. For example, this one was written back in 1982. That's a long time ago. Moisture and heat transport in hysteretic inhomogeneous porous media and so on. It's been cited a lot, and what strikes me is that just in the last 2 years, it's been cited 21 times. A paper 40 years old is still heavily cited, and I think that's quite nice. And basically, it's a study of, a numerical framework for analyzing not just how liquid water moves up and down the soil column, but also liquid in its vapor form and how that's affected by things like heat conduction and heat gradient or temperature gradients and so on. So it's a much more complete analysis of water motion in the soil. Another example from that time period is this one, cited 147 times, 9 times just in the last 2 years. And this is basically, he looked at how important are these different effects, like the thermally induced vapor concentration gradient, for example. How important is that to get right if you want to model water transport in the soil? And I'm happy to say that Chris found in his test that you can neglect a lot of these really complicated things and still do reasonably well, which is really nice to know, because if we had to include all those things, I think we'd all be bogged down a lot in terms of computer time and so on. So this, I think it was Ram mentioned this one, the potential evaporation paper. This is kind of special to me because this was really the first paper, really substantive paper that I reviewed as a reviewer of papers. Chris, you probably don't know that I actually reviewed this paper and I gave you, you had to respond to my comments. Sorry about that. Also, I showed this picture because it's a photograph of a reprint, and some of the younger people listening today may never have seen this, but basically when you wrote a paper, they would print out paper copies and you distribute them. There were no PDFs back then. But anyway, this was an important paper, as Ram said. The basic idea is that the concept of potential evaporation as applied in early GCMs was flawed. Potential evaporation computed with the GCM's current surface temperature. If you have soil moisture stress, then of course the temperature is going to go up because you have less evaporative cooling, and that kind of inflates the potential evaporation that you compute. And it makes much more sense to use an equivalent wet temperature. What would the land surface temperature be if it had been fully wetted? Key your evaporation calculations to that instead. And that was wonderful to read as a reviewer. Yeah, he's right. And I learned a lot, and as Ram said, it affected the field a lot. The generalizations of this result in areas of water stress, this potential evaporation has little physical meaning. It's just a stepping stone calculation on the way to computing ET. And a lot of people do recognize this, but there are some, and this paper was all highlighted earlier, but there are still some people I've seen in the literature where, they use things like the Palmer Drought Severity Index that's key to projections of temperature change associated with water dryness. And I think things get very misinterpreted even today because people don't recognize, or some people haven't followed up on what Chris has been telling us. The water balance studies, I'm going to talk about this one a little bit. This paper, Climate, Soil, Water Storage, and the Average Annual Water Balance. And I'll just read this. This paper describes the development and testing of the hypothesis that the long-term water balance is determined only by the local interaction of water supply, demand, as mediated by water storage in the soil. And this is such a beautiful idea that people hadn't really dealt with before this, but I can't help but show you just how beautiful it is by some examples. This is Boudico's curve of evaporation divided by rainfall, annual values, long-term climatology. And on the x-axis is an aridity index with radiation on the top numerator and precipitation on the denominator. So as you get higher values, you're more and more arid. And Boudico basically did some observations on this plot, and he fit this curve to it, and the curve has this form. It's kind of a complicated form. I've never seen a tanh used anywhere else before in science. But from Chris's 1994 paper, he says a physical theory describing the departure of curve C from these asymptotes has not been advanced in the hydrological literature. Are there factors other than the aridity index that affect the water balance in a systematic way? That's a very important question that he's addressing. First, note that if only the annually averaged climatological values of precipitation and energy supply were important for controlling evapotranspiration, then you'd have basically this curve here, this heavy red dash curve. Because when you're in the very arid region, then the evapotranspiration would just equal the rainfall, and you'd basically have this ratio would be 1, and you'd be along this curve here. And if you're wetter, then the water amount is no longer limiting, and now energy is limiting, so that you'd be along this line here. And that's, of course, this heavy solid red dashed line is not what we see, and Chris was addressing why is that. Well, if you take a seasonality into account, then during the time of the year when energy is limited, you'd be on you would be on this part of the curve here. Then, in this idealized example, during the time of year when water is limiting, you'd be limited by rainfall, and you'd be down here. You'd integrate this part of the curve, and then later on, when again if the radiation is limiting, you'd be limited, and you'd be following this part of the curve. So you would integrate this purple part of the curve. But merely Chris postulated sensibly that if some of the rainwater that falls in this time period that's energy limited is basically stored in the soil and stays in the soil, then evaporates during the time when you're water limited, then you can bring this curve up from this dash curve to this dash curve. You can actually bring it up to the Boudico curve. I thought that was a very beautiful, simple, and finally Chris was there to demonstrate it to the world, this simple idea. Oh, he also looked at other things too, like temporal variation of precipitation and land surface properties and so on. But I like to think of this very simple, this simple picture here is what he was getting at, and it really is a nice description of basic controls over evapotranspiration. He also looked at these in the context of GCM experiments, sensitivity tests. He didn't just work on pencil and paper. He actually ran GCM experiments, and I couldn't resist putting this slide up here to show how coarse resolution we dealt with back in those days, which is kind of funny. But obviously, it was a nice study with heavily cited. Now I come to the point of his career where I was lucky enough to actually work with him on a project. Ann Harrison Sellers led the PILPS project, and the idea of PILPS was you have all these different land surface models contribute to. Geez, I hope you can actually see the slides and not this thing. I apologize if that's been up there all this time.
No, we see your slides. Whatever you removed was not visible to us.
Oh, good, okay. So anyway, what they did was they had all these land models plot the latent heat flux that they get from their model when force was a meteorological forcing against a sensible heat flux. And you see from this plot that there's a wide disparity in how these land models performed. And that's the first salient result of PILPS, basically, was This intercomparison experiment showed that the land models behave very differently. And let's see here, excuse me. So I remember riding in a cab with Ann Henderson Sellers and Chris. It might have been Japan, I'm not sure. But we were discussing whether the problem with PILTs and what are we going to do about this disparity amongst the models? How could we address it? And we convinced her that we needed to do some experiments where we carefully control how the land models behave. Do a set of experiments, for example, where they're forced to all have the same albedo, something that wasn't actually enforced, where they all have the same interception loss characteristics and so on. Basically, a series of controlled experiments so we can actually get at how the models behave and why they behave differently. And basically summarized that discussion in the context of PILPS phase 1C, which is how we try to address this model disparity. Yeah, Chris studied the first initial inputs to that phase 1C and was able to demonstrate higher consistency when you start controlling factors. So later on, we had this conversation. I'm paraphrasing here, but basically I said, hey, Chris, what do you think about these ideas for analyzing our experiments? And he said, well, they're a good start, but well, he kind of hemmed and hawed a little bit. I said, but what? Well, they're missing something important. And, you know, naturally my spirit sank a little bit. Really? Go ahead. Tell me. I can take it. And Chris pointed out, yeah, mathematical rigor. That's what we need to add to all this. And again, this is a paraphrasing of our conversation, but it really struck home that Chris really drove home the point that what we needed to add to our analysis was a distinct level of mathematical rigor. And really a nice paper came out of that study, and I attribute its success to Chris's insistence on a sensible mathematical framework for the analysis. I wasn't sure exactly how far the early years ended. I put this slide up here. Excuse me. I put this slide up here because it's on the tail end of the early years, I guess. His modeling paper is this LAD model, and I'm not really as appropriate to talk about the model development as Tom, Elena, and Nate are, and I'll let them address his modeling contributions in coming talks. But this is my understanding. Chris's LAD model, along with the LM3V, were merged somehow into LM3, which became LM4. And I'll let you guys address that in the later talks. But to summarize, Chris's early papers through about the year 2000 have had, and if you look at their citation records, even in the most recent years, they continue to have a substantial impact on hydrological science. And on a personal note, I can say this, through our collaboration, Chris's approach to tackling scientific problems forever influenced how I go about it myself. And I'm sure he's had that impact on others as well. And here's a picture of Chris and I with our former advisor, Peter Eagleson, about a year before Peter died. And that was a really nice trip, and I really enjoyed that trip with Chris to visit him. And that's what I have to say today. Thank you very much.
Thank you, Randy. And I'm just going to let Chris, you take it away. I'm sure you have comments.
Andy, I think with some of the creative rigor stuff, you're projecting some of your own thoughts onto me, but I'll take them. But the one thing that came to mind during your talk, am I coming through?
Yeah.
Yes.
During my talk was, during your talk, see, I get us mixed up sometimes, was, you know, there was this recent thing, people probably saw it in the news, it was in Nature, I think, about how, you know, new science, like disruptive science, you know, has been on the decline for decades. And you could debate a lot of what they were saying, and they also tried to explain it. And one of their explanations was that people are no longer standing on the shoulders of giants. Not that I'm a giant, but people are not paying attention to the work that's already been published. And you touched on that with the issue of how we transfer climate change information into hydrologic models. And I'll be talking about that also later on. So thanks for that. And thanks for your talk, Kurt.